We're going to take a look at one more integration technique for us. Very, very useful technique, and it's called integration by parts. Now, the idea for integration by parts, this is really what's called a reduction algorithm, which means we just don't do one or two steps to get our answer. We're going to keep doing steps and try to reduce the problem to an easier and easier problem until we can get to the answer. Now, you can kind of think about this. For those of you who remember how to do like long division, 0, 8, 4, 2, something like this. We didn't just jump and say, you know, it's 10,842 divided by 4. We did it in pieces, right? We said, okay, 4 doesn't go into 1, 4 goes into 10 twice, and that gives us an 8, and then we subtract. And notice we reduced our number down to a smaller number, and then we keep going to reduce this thing farther and farther and farther. That's kind of idea what I mean by a reduction algorithm. Now, integration by parts comes from this idea. We know, I'm going to do this in differential notation, the derivative of two functions multiplied together. Now, this would be our product rule. So it'd be kind of like u times the derivative of v plus v times the derivative of u. Now, I'm going to rearrange this just a little bit, just so you can kind of see this. I'm going to move this v du to the other side. So I'm going to go the derivative of u times v minus v du is u dv. So all I do is scoot that over to that side. Now I'm going to integrate both sides. It means I got to integrate everything. Minus the integral of u dv. Now you're like, okay, great, that doesn't really look any better. In fact, that looks worse than what we started with. But this piece right here is the reason we did it. This is the derivative of something. And we know if we integrate the derivative, those two kind of cancel each other. And what we end up with is uv. Now you're like, what do you mean that's what we end up with? Well, this is actually our by parts. I'm going to write it the other way around. It says the integral of u dv is uv minus the integral of v du. You're saying, okay, not only do I not understand that, that doesn't look like that's going to make my life easier. Well, it kind of does. Here's what it says. Remember, u and v are just functions. So this says if we're integrating two things multiplied together, then the answer is going to be one function that's already integrated, right? That piece is out of an integral minus another integral. And the idea here is hopefully this new integral is easier than the one we did. So we were able to integrate a little bit and we still have some left. All right, let's see how this works. It's not as bad as you think it would be. So let's say we were going to integrate x squared e to the x. Okay. Now, you would always go through the same steps you always do. You say, can I integrate this directly? No. Can you rewrite it? No. What about a substitution? You know, like a UV substitution like we learned in the past. Nothing like that will work. The key here is notice we have two different types of functions. We have a polynomial times an exponential. That's a pretty good clue that by parts might work. So what we need to do is we need to pick the two pieces on this side. Well, technically we're only going to pick one. We're going to pick what we want u to be. Then everything else in the integral is going to be dv. Now notice on this side, we need uv, v, and du. So what does that mean? On this side, if we have dv, that means we're going to have to integrate to get v. If on this side we have u, and over here we need a du, we're going to have to take the derivative of that. So we're going to pick one function that we're going to take the derivative of, and the other one we're going to have to integrate. So what you normally pick is pick the function that's going to go away when you start taking derivatives, or it gets less complicated. See here, if I let u be equal to x squared, right? I know when I start taking the derivative of x squared, what would it be? It would be 2x, and the derivative of that is 2, and the derivative of that is 0. Notice how it kind of goes away. So that's how you want to think about this. Now everything, that's the only choice you get to make, what u is. Everything else up there is dv. Okay, so now this is where students get confused because we're doing two different things right now. On this side, we're going to take the derivative, and I'm going to use differential form. So du is 2x dx. Over here, I have to integrate. So v will be equal to the integral of e to the x dx. Well, that's one we know. That's just e to the x. Okay, so there's kind of the side work that we need to do here. Now we can put all this together, and it's actually pretty easy. We're going to use our formula, right? uv, so this integral is equal to u times v minus the integral of v du. That gives me 2x e to the x dx. uv minus the integral of v du. Now, we managed to integrate a little piece, but now we can still have an integral to do. But now notice, this one's actually a little bit easier to do because that started out as an x squared. This is just an x, which means we're going to want to do by parts again. Now, if we could integrate this directly, we would go ahead and do it, but here we're going to do by parts. So let's let u be our 2x. Everything else is dv. So the derivative of this is just 2. The integral of this, and if it's an easy integral like this, you don't necessarily need to write the integral. I know the integral of e to the x is e to the x. Okay, so what do we get here? I get x squared e to the x. That part we're done with. Minus. Now you need to use parentheses here because I'm getting ready to write this one integral as two pieces. Okay, so uv, so 2x e to the x minus v du. So what do we have? V du. So that's going to be the integral of 2 e to the x dx. Now I'm just going to move it up here for a little bit of room. So we have x squared e to the x. I'm going to go ahead and distribute this real quick. Minus 2x e to the x plus the integral of 2 e to the x dx. Okay, so all I did from the bottom to the top is just distribute that negative. Now notice we still have an integral to do. This one we can actually do, right? The 2 is a constant, so we don't have to worry about that. The integral of e to the x is just e to the x. So we have x squared e to the x, 2x e to the x plus 2 e to the x, and of course, plus c. All right, so by parts is a reduction algorithm. The only choice you get to make is what u is. You generally pick, most of the time, if there's a polynomial involved, most of the time, the polynomial is what you're going to let be u. Everything else is dv. Take the derivative of u, integrate dv, and then plug it into your formula. You got to memorize this. uv minus the integral of v du. Plug it in, and then it's like a brand new problem now. Take a look at that new integral and say, how do I integrate it? Well, if you still have basically the same thing you started with, polynomial times an exponential, polynomial times an exponential, you're going to keep doing by parts as long as each consecutive integral gets, well, less complicated. And eventually you'll be able to finish up that last integral. All right, let's try another example. Let's make it easy. Let's do something like, I don't know, x cubed ln x. Okay, so if we're told to integrate this, again, you're following all of your steps. I don't know how to integrate this directly. Excuse me. Don't really see a substitution that would work, but I'm thinking, hey, maybe by parts, right? Because I got two different types of functions. I have a polynomial and a logarithm. So you say, well, I'm going to do by parts. And Mr. Bentley said, if we see a polynomial, we're going to let that be u. Don't copy this down, by the way. This is going to be wrong. So, and everything else was dv. So dv is the natural log of x dx. Well, that's fine. That works out great over here. du is just 3x squared dx. The problem is, what is the integral of the natural log of x? The answer is not 1 over x. That's the derivative. Actually, we don't know how to do this yet. We will in a few minutes. But as of right now, I don't know how to do that integral, which means I can't do it this way. So if it doesn't work that way, try it the other way. Let u be the natural log of x. dv would be everything else, x cubed dx. We take the derivative over here. Now the derivative of the logarithm we know is 1 over x. And the integral of x cubed is 1/4 x to the 4th. All right, so let's put our pieces together. We know the answer is going to be uv. So u times v is 1/4 x to the 4th natural log of x minus the integral of v du. So that's going to be 1/4 x to the 4th times 1 over x dx. Now let's clean that up a little bit and see what we actually have. That's going to be 1/4. One of those x's is going to cancel x cubed dx. Now the 1/4 is a constant. If you want to write that out front, that's perfectly fine. So let's see, we have 1/4 x to the 4th natural log of x. Now this integral, we should be able to do that, right? Add 1 to the power, divide by the power. When I add 1 to the power, I get an x to the 4th. When I divide by that, I already have a 4 on the bottom, so that gives me a 16. And there we go. So kind of clue here is, yeah, most of the time our u is going to be the polynomial. However, if you see logarithms around, there's a good chance that's going to be your u. Now we did run into a problem in this example that we can actually solve now. Here's something that we don't know how to do yet. What is the integral of just the natural log of x? Well, we're going to do it by parts. And I know you're thinking, I thought you said to do by parts we needed 2 different functions multiplied together. And here all we have is 1. Well, technically you do have this. Right? We have 1 times that. And since 1's a polynomial, it actually fits exactly the same as this one. Right? We're going to let our u be the natural log of x, and dv is just 1 dx. When we take our derivative, that's going to be 1 over x dx, and v is just x. So when we put this together, uv, we get x ln x minus the integral of v du, so it's x times 1 over x dx. When we simplify, that's just the integral of dx, right? Those x's cancel. Well, now we got to an integral we can do. The integral of dx is just x. All right, so here's good news slash bad news for you. Since our natural log is one of our basic functions, you can, if you want, just memorize that that's the integral. So on a test, if it says the integral of natural log of x, I would allow you just to go ahead and write that down, right? It's one of our functions we should just know the answer to. However, you got to remember, if you don't memorize it, you got to know how to do this by parts. All right, now by parts, as you can see, can get pretty long and have to do a bunch of steps to actually get to our final answer. I mean, the very first example we did was something like this, was like x squared e to the x, right? And it took us by parts, like 2 by parts and another integral to finish that up. So like 3 whole sets of steps to get through that. So what if it was an even harder one like this? What if it was like the integral of x to the 4th e to the 3x? You go, oh man, that's going to take me forever, right? It's going to take me at least 4 steps in another integral even to get there. That's going to be a whole page worth of work. Well, when something has this form, again, notice I have a polynomial times an exponential. You have a polynomial times an exponential. There's actually a shortcut method to do this, and it's really, really helpful. It's called the tabular method. And technically, the tabular method will work with any 2 types of functions as long as one function goes away to 0 when you take its derivative. So we're going to set up a table. It's the tabular method. We're going to have 3 columns. The first one's a sine column. The second one's a derivative column, and the third one's going to be our integrate column. Now for your sine column, we're just going to alternate plus or minus down for a few here. Plus, minus, plus, minus. You'll get the idea of how many you have to go after a while. In the derivative column, you're going to pick the polynomial. And in the integrate column, generally the exponential you're going to integrate. Now, do the derivative column first. Take derivatives till you get down to 0. So that's 4x to the 3rd, 12x squared, 24x, 24, and 0. The integrate column, remember if we integrate, remember our rule, if we integrate e to the ax dx, that's 1 over a e to the ax, plus c of course. So if I integrate e to the 3x, that's going to give me 1/3 e to the 3x. Now I'm getting another 3 that comes out, so that's 1/9 e to the 3x. 1/27 e to the 3x, 1/81 e to the 3x, and you just need to go down to your even with a 0. So I need one more, so 1, let's see, that's 243 e to the 3x. All right, now I got good news and bad news. Actually, it's all good news. Now I'm lying. We're done. That's all the work we actually have to do as far as calculus. The rest is just putting the pieces together. Now here's where it gets just a little tricky, not tricky at all, just, I mean, as far as what you got to do. What you're going to do is you're going to read across the first two and then go down at an angle. So my first term for this integral is those three pieces. So I'm going to put the equals way over here. So positive times x to the fourth times 1/3. So that's going to be 1/3 x to the fourth e to the 3x. That's our first one. Then you keep doing this until you get down to you get 0. So I go across and down. That's going to be a negative 4x cubed times 1/9 e to the 3x. That's going to be minus 4/9 x cubed e to the 3x. And you just keep going. Now, I'm not going to reduce these fractions as we go. You probably should, because this next one will definitely reduce. So that'll be plus 12 over 27 x squared e to the 3x. See, minus 24 over 81 x e to the 3x. Crossed and down. So that's going to be, oh, no, that's right. 24 over 243 e to the 3x. Now notice everything after that, since all these derivatives are 0, would all be zeros. So that's it, plus c. Now notice how long and ugly that answer is, and can you imagine trying to carry those fractions through doing partial fractions? I mean, by doing by parts the entire time, it'd be very, very messy. So this is a very nice, easy technique for when you're integrating, especially a polynomial times an exponential. There are other functions you may learn in the future that this works well on, but for right now, you should probably stick to this combination to make your life a lot easier.